the virtual work method. All right? And this is the answer to what is this virtual work method and how do we actually use it. All right. I know that, we took the virtual work theory way back in kindergarten, right? So maybe it's time we refresh a little as to what it is, all right? So this is what it is. Say you have a two-dimensional frame, all right? Two-dimensional frame, nice 2-bay, 5 stories, 10 stories, whatever you wish. Two-dimensional frame, subjected to lateral load, all right? Under the influence of the lateral loads, the structure is going to deflect, all right? And if you look at any one particular beam in that structure, or column for that matter, and you look at the joints, at the joints you will have a bending moment, you have a shear force, and you would have an axial force, right? You have vertical rotation, a moment, a vertical shear force, and an axial force. Corresponding to that, you have a rotation, a vertical displacement, and a horizontal displacement, right? Now, if you take the moment, multiply it by the rotation, take the vertical shear force, multiply it by the vertical displacement, and take the horizontal force multiplied by the horizontal displacement at each end. Namely, you've taken out a free body diagram of that beam, taken the displacements, multiplied them by the corresponding forces. Moments by rotations, displacements by the forces. And you add those numbers together. Moment times this rotation added to force times this deflection for each component at each joint. So what do you have? You have work done. Rotation times the moment, vertical force times the vertical deflection, horizontal force times the horizontal deflection at each joint. You add them together, you get this quantity which is work done. Force through displacement is work done. And that is a measure of the energy that is in that element. If you divide that energy by the volume of the element, you get a number which is work done per unit volume. All right? It's essentially the energy in that object per unit volume. And you go through the same exercise for every beam and column in that two-dimensional frame. Is it clear so far? So we get energy per unit volume in every element of that frame. Okay. What does that value mean? That value is a measure of how much work every element is doing in order to resist that lateral load that we apply to the structure. So the elements that have more energy per unit volume are working higher, are working harder. All right? So far so clear, right? Very, very clear, no problem. That's our virtual work exercise or virtual work tutorial. Now, say that now under the influence of this lateral load, that frame is displacing too much, just like this was. It's displacing too much. And I want to strengthen that frame by adding more material. Say it's deflecting 3 inches, or in this case 1.3 inches, and I want to bring it back to 9/10 of an inch. And I've got this extra steel sitting in the garage. And you come to me and say, yes, we have this frame, it's deflecting too much. But I have this extra steel sitting in the garage that I would like to bring out and put into this frame. Can you tell me how I should redistribute that material into this frame so that I get the most efficient use out of that material. So the question becomes obvious. The question is, the answer to that question is, actually the answer becomes obvious. The answer to that question is that you take that material and you redistribute it into that frame in proportion to the virtual work per unit volume being done by each member of that frame. It's just like a bonus system. You know, when you're running a company, the people that are working the hardest, you give them a larger bonus. So you take that steel and you redistribute it. And then how do you redistribute it? I mean, do I change the moment of inertia? Do I change the axial area? Do I change the shear area? Well, you know that also, because when you calculated the virtual work, you did it according to component. You had a moment component, you had an axial component, and a shear component. That determines which property of that section you are going to change. And by how much? It's just by a ratio between the deflection that you want and the deflection that you calculate. So each property, each component of the property, named the shear area, or the axial area, or the moment of inertia, gets a factor on it, coming from the ratio of the required displacement versus the target, the actual displacement versus the target displacement. And then you just go looking through the properties for a section that satisfies that higher shear area, higher axial area, and higher moment of inertia, and you replace that member. And you report back saying that you have a changed member, and this is the size. And when you reanalyze it, boom, you find out that you got a structure that satisfies the deflection criteria. But you can see that the theory is so simple, nothing to it. But it saves an incredible amount of time.